So the chain rule is the proper rule for differentiating a composite function. And in terms of notation, we have to be a little bit careful. So when we see something like this written, we should think of it as follows. It would be the derivative of all of this stuff. And that's how it would look in prime notation. But you have to be careful that that expression is a little bit different than this expression. So this would be f prime of x evaluated at x is g of x, which is just f prime of g of x. These two are not the same. At the same time, when you are asked to differentiate a composite, another way to write it would be like saying the derivative of f circle g of x or f circle g prime of x. Those, in fact, are the same. So chain rule is nice because chain rule allows us to get results for things in usually a more straightforward way than we could with product rule or quotient rule. So for example, when we see an expression like this, we always have to make a decision. We could think of this as a quotient, because it certainly is a quotient, and we could use the quotient rule if we wanted, but it might be of use for us to understand that this could be written as a composite function. And then the question is, well, what is the composite function here? How are we treating this? You could think of this as the derivative of x squared plus 1 to the minus 1. And when it's written like this, then I'm hoping you can see clearly that this is the inner function, u, and this is the outer function. So the outer function in this case would be u to the minus 1. As take the derivative of the outside layer, so we would be taking the derivative of essentially u to the minus 1, and then we would take the derivative of whatever u is. And in this case, we would get negative u to the minus 2 d by dx of u. Now we resubstitute for u. The u is just a temporary placeholder. And we would now come up with the full result like this. Here. Minus 2. The derivative of x squared plus 1 is 2x. So at the end of the day, this is going to give me negative 2x over x squared plus 1 squared. And you can compare with the quotient rule, and you should get the same result as you would have gotten doing it this way. This way is likely quicker and more convenient for most people. So this is a very useful feature of the chain rule, that it allows you to differentiate powers of composite functions like this very easily. The chain rule doesn't have to stop with just a single function substituted inside of another one. It's possible for you to use the chain rule for multi-level composite functions. So in fact, this expression right here is a composite. And it's probably best for you to think of it using the more suggestive notation here. So the square power on that tangent is in fact the entire expression squared. So this is a composite function. This entire expression here will be the inner part. So we'll say that u is tangent of 3 theta. And then the outer part would just simply be u squared. So according to the chain rule, that would give us 2 times whatever our substitution is, times the theta derivative of our substitution. Now, normally we would have a u there, but we don't necessarily need to write that u in. And in fact, if you get a little bit more comfortable with it, you end up skipping that part. And this is, I'll put it in explicitly here, this is the derivative of the outside layer. We've done one level of onion peeling. We've differentiated the outermost layer, the square power, but now we're left with a new derivative. So it's almost as if we've been asked to calculate something from scratch again. Now, how we do this? Well, this is also a composite. So this time the inner layer, you could call it something else. You could say it's V. It would be 3 theta. So according to the chain rule, we would have our outside layer where it was before. The derivative now, the outer layer that we've got, is the tangent of V. So the chain rule says take the derivative of the outside layer with respect to whatever letter you've chosen. So the derivative of the tangent of something is secant squared of something. And then the chain rule tells us we have to differentiate that something, the inner layer. And now you can start to see that the expression is a chain. It's this long connection of the derivatives of each one of the layers of this composite function. So the final step is that we try by convention just to group all of the constants in front, and we end up with something like this. If you have a 3 or 4 level composite function, you take a look at your answers after each stage and reassess and say, can I use the chain rule? Should I use the chain rule? And then apply it from there. The chain rule is the most important rule that we've got out of our differentiation, and it will get used over and over again from here on in the course.